Hello and welcome back to your third problem session. We have an audience member today, so you might be standing in for you if you weren't able to be here, which, well, I guess most of you weren't. Nevertheless, today we are going to review the second exam, so go through all the ones that most people had trouble with. If you found that you were having trouble with a section I don't go over, feel free to bring it up. Lastly, we will go through some problems from Chapter 3. These are some that I thought just were maybe a little different than what we've done, or some examples of ones that you've seen before with different chemicals. So you can get a sense for using different masses and coming up with your molar masses and such. And so we'll kind of do two parts for today. The first thing I will say is as we go through, this is the exam, second exam, know that you'll really need a periodic table to help you out. So know that you've reached a point in the semester where when you're doing your homework, you'll either want to have your textbook or at least one up on your computer. It'll be pretty hard to begin to do some of this stuff without that as your resource. And so again, know that I never expect you to memorize any of this stuff. It should always be there and you should be able to interpret it that way. And we'll do some of that early on with the test as well. And then lastly, Chapter 3, there's a bit more math, right? So I would say have your calculator ready as you're following through with this, and also as you work through your problems. You should never torture yourself to do that math alone. And so I'll read through, again, just some of the ones I noticed people had more trouble with. So this is starting with Exam 2. And let's look at question 1. So here we were just sort of looking at the periodic table. And I had you guys circle and change some of the things that were on here. Just to show me that you had an understanding of sort of how to bring information out of the table. That, of course, is what I'm most interested in. You can get through this course with really just a table and a calculator, if you think of it that way. You just need to sort of know what information's in there. So the first one we saw were the noble gases. Let me try to bring this a little forward. And so we have a couple of features of the periodic table here. We have the understanding that the premise of it is that every period or every kind of column that you hit as you go over, you have similar properties. And so the noble gases are our first set of different elements that all have the same properties here on the far right. So these are going to be things like helium, which, right, we use to fill balloons, things like neon, all those gases, right, that you're somewhat familiar with. You may also remember, right, that we have mostly metals on the left and then also moves towards gases on the right. So you should have maybe looked in that area to begin. From there, one of the biggest misconceptions so far, challenges that I've seen, are understanding the charges of these systems here. So let's look. I'm actually going to literally fold this to make it simple because I'll show you exactly the only charges I expect you to remember. You may remember that when it comes to the transition metals right here in the center, that those have multiple charges. And so it doesn't actually, well, you don't need to memorize those just yet. You never will. Probably not as engineers, but that's not the point. Okay, so doing a little bit of origami here, which on a test you'd also be welcome to do. You can see we have a kind of shorter version of our periodic table. And now what we're going to do is talk about the charges. So we're now going to talk about, what is it, question B. So 1B on the exam. So again, if there's those kind of periodicity or that similarity between the chemistry of each column, you can guess that the charges are going to be the same for each of these. And so what we find the pattern is that we have a charge of +1 on the left, +2, and then +3, and then carbon is where it shifts, and we go back down to -3, -2, -1, and then these noble gases, they're noble because they don't react, and so they have a charge of 0. So let me actually label this just so you can see it clearly. This is, right, you can pull it from the table, but you do kind of need to know where to start. So I always like to think of hydrogen and water as +1, and oxygen is -2. So I've always found that helpful as a way to kind of set up the scale. So to point that out again, right, we have hydrogens at the left at +1. Let's get you started. And then you can also do oxygen at -2. And again, we're thinking here that H plus, or two of those, plus O2 minus is H2O. Which I guess I could be writing on the board. And so the premise here is that you set up your +1, +2, +3, -4, and then oxygen is also -2. So it's kind of like setting your boundaries of what you need to know. And then again, anytime you hit something in the center, the transition metals, I'll give those to you. And you noticed at the bottom of the exam, that was part of those as well. I realize you guys can't see me. What else? Most people got that right next to the gases are the halogens. What some people may have had some trouble with was realizing that the heaviest halogen, which the question asks for, is just going to be the one towards the bottom, right? Hydrogen we know is very light. Those are the gases that float. And then on the opposite side are going to be all the very heavy things. Radon is that gas that sits in your basement. So that's going to be a gas, but also very heavy. So you can think to the top left, you have light and gaseous. And on the bottom right, you have heavy, definitely, and probably somewhat metallic as well. Okay. Everything else was pretty okay. I was pretty liberal in my grading of what people thought were elements that were not found on Earth. Many people circled a lot of radioactive elements, which they may have received partial credit for, in part because they are on Earth, but probably not for a long time. So it was a good guess. Answers that I would be looking for include things like technetium, really anything without an atomic mass with lots of numbers on it, right? Which means we literally can't measure it. It doesn't exist naturally on Earth in that way. So at least on the table I gave you for the exam, that could be, a lot of people circled things even without letters. I guess they're kind of faint in the way it printed, but nevertheless, even things like, francium and things like that, right? We don't have lots of digits, and so that's a sign that they're still natural in the terms of the universe, but they're not natural in terms of you could go to the store and get them if you wanted. I'm going to jump just a little bit to question 3, which is chemical reactions and balancing, only because it ties in really well with the chapter we're working on. So let's do both of these different equations, and we'll see why some people were so frustrated with the second, in terms of balancing, at least. And I'm not sure that one has an answer necessarily. So the first thing I'll do is I'll just always write out whatever the reaction is. So that's just the left side of that first reaction. And then maybe even separately, I can write down the second half, right? The premise here being that they're going to have the same amount, if they're balanced, I should say. And there were lots of questions about which atoms and elements the numbers refer to, so we'll go through that in just a moment as well. SiO2 times 4H2O, and then we have plus 3 CaOH2. So your real goal is to come up with the number of calcium, silicon, oxygen, and hydrogen atoms, and then we'll balance it with the number on the bottom. And so it is a little challenging, right? One thing, for example, you might want to say separate out your different molecules, right? So this is all one thing, and so in this case, let me make sure I'm getting this right. Yes, this 2 is affecting everything from there to there, just as the 7 is affecting both the H's and the O's. And so, for example, when we begin to do our math, we can say that we have 3 calciums here, multiplied by that 2 to give us 6. We have only 1 silicon times 2 will give us 2. And for now, we have these 5 oxygen also multiplied by that 2. And that's where that 2 will end for us. So 5 times 2 will be 10. And we'll have some more oxygens in just a moment. We'll start with hydrogen. So here we have 2 hydrogens multiplied by that 7 to get 14. And then we have 7 times those oxygens as well to give us a total of 17 oxygens there. So I'm just adding those up. Next, we'll do the bottom, and hopefully, if it's balanced, we wouldn't even need to, right? The atoms would be the same top and bottom. So the first thing we can see, right, is that some chemistry did happen. We can see, for example, right, we had 2 Ca3, and now we're at a singular calcium, so something interesting. Again, I think this relates to cement setting or something to do with concrete. I know those are different. I don't know why. Nevertheless, let's do it again. We have our Ca, our Si, our O, and our H. And I always like to argue that the hardest part of any problem in our chemistry class is just going to be setting it up, right? After you do that, the math is the thing that you can do again and again. But if you have the wrong setup, you won't get very far necessarily. So let's work our way again. Here, unlike what we had before, we have to think that the 3 only affects the Ca, right? Because technically there's also that dot in between, kind of like a hydrate, right? We see the hydrate here, but here the silicon it's kind of its own thing. So we can think of the 2 affecting just what's in those parentheses, and similarly, just like the 4 only affects the H2O, it doesn't keep going there. So let's go one by one. We have 3 calcium from this first one. We have 3 oxygen. We then have 2 times the 1 silicon for each. We also have 2 times the 4 oxygens. So, right, we can see oxygen is pretty separated in these. That's part of what oxygen does. It's very good at that. I haven't done our hydrogen yet. I know that because there's nothing there. So 4 times the 2 hydrogen per water. That's going to be 8. And then lastly, 4 times the oxygen. So we're going to have 4 more. And so before we do the last piece, let's see what we're missing. Maybe we can find that that's what's in our last component. So you notice there's a difference of 3 calcium between what we had and what we are at. We've counted for all of the silicon, so that's pretty good. We would hope that there's no more silicon in this, which there is not. Last but not least, we have had 17 and we're at, that's 11, so we're not there yet. We're looking for 6 oxygen, and hopefully you can see that is in here. And then lastly, we're missing some hydrogen as well. So let's finish this up. Now what we're going to do is see that the 3, again, affects everything inside, and the 2 here only affects what's in the parentheses here. So again, your parentheses, even if they're not shown, are going to be a helpful way to kind of think about what's together and what is not. So now let's try to do it. Well, we have 3 times that Ca. That's going to get us to the 6 that we had up here. Then we have to think, right, there's 2 of these. So this 3 is multiplied by the 2, and conveniently there's only 1 of each. So that means there's 3 times 2, or 6 of each of these. And so we can see our math is beginning to finalize. That was, 6 I was saying? And so we can see we have 6 total of the calcium, 2 of our silicon. We have 17 here. We also have 17 here. You can see that? You can. And lastly, we have our 14. And so we can see that everything that was on the left is now on the right, just kind of in a different form, right? Parentheses shifted, numbers shifted, but it's still the same thing. And so I would say one of the things you should practice is just thinking about what is kind of contained on its own, and we'll see that in a moment with some of the other examples later on the exam. So, as you may have already known, this is balance. And if you're questioning what I'm looking for on your exams, I would just want the equal number on each side, clearly written, hopefully. Maybe the word balanced as well, that would be nice. So now let's do the other reaction. So this was part A, this is now part B. This is just the second one in question 3. And so here we have something that you may guess may not be balanced. Even by looking, sometimes you can sort of tell. And I'll put parentheses, sorry, that's a calcium, just to help us out to start. I know, my 5s are pretty bad as well. I'll practice those. Do I have? Yeah, I have a lot of room. Okay, so that is the left side of the reaction. Oh, and now let's put the bottom down here. That makes it easy. It's kind of similar reaction, right? Up top we started with Ca3, now we're at Ca2, but at the end we're getting to, anybody know what this is? I know there's an audience member. This is known as lime. This is a component of, well, you can burn like mussel shells and things, but if you've ever heard of the limelight, like stepping into the limelight, they used to burn this and it would shed light on performers in the theater. Bet you didn't know that. Nevertheless, it's also very relevant and very reactive, so be careful. Last but not least, we have something sort of from the first reaction, right? The silicon dioxide. We have our, and then lastly, right? And so you can kind of see what we're looking at in different reactions, right? Up top, we looked at 2 different things, right? We had silicon with 4 oxygens versus with only, versus with 5. And yet here we're looking at almost the same products, right? So the balancing will be easy on this end. Maybe we'll do this one first. But we don't seem to have as much for some reason. Maybe this number's missing, for example. We'll balance in just a moment. Okay, so let's do this. On the bottom here, right, we're going to write out our elements individually. Doesn't really matter which order they're in, but I'll write them in the same as the other side so it's a little easier to see. And we can do that over here as well. And let's do it. So we have in this component, right, which again is in these parentheses, right, the 3 is only affecting the CaO. We're going to have 3 of our calcium. We're going to have 3 of our oxygen. we have 2 silicon, and we have 2 times 2 oxygen, or 4. And then that's oxygen down here. And then we have 4 times 2 hydrogen, or 8, and then 4 more of these oxygens. That's a 4 I'm supposed to write. Right, and so far it looks pretty much like what we have on the left side, right? We have a 3, we have a 2, we have a 3, 4, 4, we have an 8, but we can see it begins to change, right? And so just to be clear, we're not balancing A with B, we're just comparing to kind of show what may be missing. We're just balancing what's on the top and bottom here. Okay, so we have 1 extra C. We have 3 oxygens and hydrogens separately. Okay, so let's total those up. This is going to be 11. Here we have, 6 plus 8 is 14. We have our 2 silicons, and we have our 4 calciums. And so let's go now up top. So looking at this one piece, we have 2 calciums, we have 1 silicon, we have 4 oxygens, and then we have 5 times 2 hydrogens, that's 10, and we have 5 more oxygens to give us 4 plus 5, or 9. And at quick glance, we can see this one definitely isn't balanced, right? None of the numbers actually match. We have 2 compared to 4, 1 compared to 2. We have, I think, a 9. Odd numbers are always interesting in chemistry. Similarly, we have 14 down here, and these don't match either. So something we'll do as we do some questions later is begin to balance. To give this my best shot, you might see, for example, that you have twice as much calcium down here as you do up here. So you might think to say, add a 2 in there, which would then double this. It would also double the silicon. That's 2 and 2. And it would add 4 more of these oxygens over here. So we would get 13, right? Not too bad, we're getting close. What else would we need? We would need another oxygen, and we need to get rid of 2 hydrogens. Not quite sure we can do that. I don't think we can. Oh, wait. No, because we can add. I don't think it's possible for this one. And it not necessarily is. Some reactions can't be balanced based on the ingredients you're given, right? Maybe you'd have to say change the charges of things or add in other stuff. So this would be not balanced. And by showing this work, you would have full credit on part 3 on the exam 2. And now I'll do some of the formula ones, which I knew kind of held people up. I could see that people were either very comfortable with these or sort of doing their best job. Know that it's not so much that I'll ask you these exact questions again, but later on I'll just give you formulas, and you should be expected to figure out charges from the periodic table and then also think about formulas as well. So I might even give you names, for example. One example of that is part 4C. So you were asked to come up with the equation between sodium metal, right, plus water, which is with a W, and that goes to, sodium hydroxide, and hydrogen gas. And so this really wasn't a balancing question. I didn't grade anybody based on whether they did balance this reaction. It was more of a naming question. So let's take a moment to break down what our reaction should look like. So sodium metal, which was really the beginning of the question in 4A, is just going to be represented by its atomic symbol, right? This is going to represent the base element, which happens to be, well, sodium itself is a metal. We might call it a metal because it's not boiling or a plasma, right? It's at room temperature, and sodium is a metal at room temperature. Water is probably one that you know or are familiar with. We've all seen H2O at some point and been talked about a lot in this course. So the nice thing is, right, we use not only a traditional name, but then also somewhat more of a common name. Water's special in that way. We can just call it water. Last but not least, right, we have these other components which we have to think about. So the first would be, without even looking at charges or balancing, we know that sodium has to be involved, right? Also, it's on the left-hand side. We can also think about the fact that we're going to want to include everything on the left on the right? So there's going to be at least some sodium, hydrogen, and oxygen, which at least, well, hopefully was somewhat clear. On the board for the exam, or printed on your exam next time, will be a table of your polyatomic ions. And so on the board, you might have seen hydroxide as OH minus. And that might remind you again that Na in that first column is going to be plus. And so the first thing we will make is our Drano. This is one of the main components, sodium hydroxide. And then most people got to that hydrogen was the product for hydrogen gas, right? Not just the symbol. But one thing we have to remember is in its natural state, right, there's a variety of different gases that all form the diatomic, or two-atom compounds, of which hydrogen is one, probably the easiest to remember. What else do we have? We have oxygen, we have nitrogen, and we have iodine, I believe, as well. And anytime you see these in a reaction, they should generally always be in the diatomic form, just so that, well, they wouldn't be found that way other ways. Whereas sodium, right, you can carve up sodium all the way until you get to an individual atom. It's a little bit more challenging to break these up, which we know, right? Nitrogen in the atmosphere doesn't really react much. It's kind of just sitting there. How are we doing? Not bad. I do want to do some more naming, so let's do some of part 5 on the exam, and then we will shift over to chapter 3 questions. Any questions from the audience? Sounds good. I'll also do a little bit of 4B. So yeah, let's do 4B first, because it's kind of quick. So these were provided to you, incorrect compounds, and we'll break down why each of them were for different reasons. So what I'm saying is none of these are correct. None of these represent anything that actually exists, at least based on the way that we formalize how things are called. The first one could be a couple things, right? Maybe the numbers are wrong, maybe the placement of the atoms are wrong, or the balance between the two. So looking back at our periodic table, we can see, for example, that, let me get this right. Where is it? So if you look for rubidium, which you don't even need to know the name, just know the symbol, right, Rb, it is down below not only hydrogen and lithium, but also sodium as well. So that should have a +1 charge. So if rubidium has a +1 charge, and chlorine, as we know, also has a -1 charge, right? It's on the far right side of the table. That means that if we combine these two, we should just get very simple RbCl, or rubidium chloride. So right here it was the 3 that was the problem, because there is no Rb3+. That just doesn't exist, at least not in a practical way. This one wasn't so bad. The nice thing you may remember, sulfur is 2-, and sodium is +1, right, times the 2 that you have there. So the good news is that the charges are correct. It's just that we always put everything from the left side of the table first before we get to the right, and we'll describe this more later in class. And so all that you needed to do here was think Na2S. And again, a good way to remember which side comes first is just think of sodium chloride, right? NaCl, that's the one you probably know. And you'll think you start on the left and then you move all the way to the right to name there. And so last but not least, we have magnesium hydrogen carbonate. And the issue with this, again, comes down to charge. So let's look at our table. We can find magnesium down here under beryllium. So right, +1, +2 is going to be the charge that we need for magnesium. It will generally always be found in that state. And then again, if we looked at the polyatomics in the reference data that you had on the exam, you would find that this is minus. So again, here it's a question of balance. And so if we want MgHCO3, we're going to need 2 of these. And then the biggest issue I saw was where the next parenthesis goes, right? And we have to remember that this is its own ion, and this is its own ion, right? This all kind of comes as 1. And so we add the parenthesis here, implying that the only thing that's 2 is everything inside. So there's 2 of these. They each have a -1 charge that balances out the magnesium's +2 charge. And so magnesium hydrogen carbonate looks like this. It can probably be bought in your local Duane Reade. Great, so let's just do a couple of the namings and then we'll be done. Overall, I thought it was a pretty good exam. There weren't too many low grades, which was nice. The average, I think, again, was between the two classes around like an 84, 85, which isn't bad. Know that this next one will be very different, right? Chapter 3, as we'll find, is going to be a lot of math, so just a different set of thinking skills in that way. Let's do it. So we're going to go from a couple names, like magnesium hydroxide, and let's do the hard one, sodium sulfate tetrahydrate. Oh, I missed the D. Become a chemistry professor and you never have to learn to spell. It's really wonderful, I promise. And then let's do two compounds, right? Let's do the iron hydroxide. And let's do this one. Okay. So one thing you notice is that there are, I think almost all these examples except one or two are all polyatomics or have components that are polyatomics, right? So you're going to be using not things that you've memorized, though you're welcome to. You're going to be using the reference data we give you. In this case, you would have had the ion and then also its name. And so, for example, you have to first just go to the periodic table and come out with everything that we have. And let's see, we were just doing magnesium as an example. It will always have the same charge in this class. Take a second to think if you can remember it, and if you can't, again, you just need to go to that second row, find where it is, and think that it is +2, or 2+, however you think of it. And so now, if we're putting together Mg2+ and OH-, let's put this guy in parentheses because we want to make sure that they're kept together. All we need to do is have two of these minus charges to balance this. And so if we add the 2 here, we can erase our charges, and we have our compound. A lot of people put, say, the parenthesis here or the 2 in front of the oxygen and whatnot. And so, again, we want to think of them in ionics, right, which is what we're looking at, ionic compounds with charges. We're always going to think of two separate pieces coming together. I guess 3 in this way, but essentially a positive and a negative side and to balance it like that. Okay, moving on to the next one. First thing I would always do when you get a name, again, is just write out all of the symbols relating to what it is. So the sulfate would have been from the reference that you had. And the tetrahydrate is probably the most confusing part. The good news is that you know that a hydrate refers to water. And then so all we have to think about again are those abbreviations, mono, di, tri, and then tetra. Tetra is one of the harder ones. You can think of things like tetrahedrons, which have 4 sides. I don't know if tetracycline has 4 of anything, but it may. And so this helps you out a little bit with the number as well. And so now again, we're going to just come and put everything together. I'll put this in parentheses just so that we remember that it's one piece. And then we're going to use that kind of large period and the 4 waters to cap it off. And so we again see that we have a +1 but a -2. So let's do 2 of the sodium to balance out that sulfate. And here we have sodium sulfate tetrahydrate. So this is your answer here. Now we have the opposite job. We're actually going to go from the symbols and the formulas down to the names. And so what I would do is the same thing, but kind of in reverse. I would write out these things separately and then see how they go together. So Fe, if you're thinking, right, number 26, or iron. And then leave a little space always with transition metals, right? I told you that I'm not going to make you memorize them, but there is also information hidden in here as to what the charges are. And so because I'm not going to make you memorize them, you will be expected still to work backwards from the information you have. So let me explain what I mean. Let's take just hydroxide before we do anything else. But now we would need to know the charge, right? Because this could be iron 2, it could be iron 3, if we just had the name. So one of the things we do with transition metals is we put the charge in here. And if you're asking how did I know what the charge was, well, if OH minus is the species on its own, and if we have two of them, we know that there are 2 minus over here, and so there must be 2 plus over here. I could have given you FeOH, is that even on the screen? Yeah. FeOH3, and then you would have known that it was Fe3 plus, right, because of the 3 OH minuses. And this would have been iron 3 oxide. Oh, sorry, hydroxide. And so I actually really only asked you guys about ionics on this exam. Some of those come between metals and nonmetals. Some of them come between transition metals. And it is only with transition metals that we need to know these oxidation states. And the way you can remember that is because I don't make you memorize them. And so thus you must get the information from somewhere else. And thus when you look at something with a transition metal, know that you will be able to pull that information from the formula when you begin to balance. And we'll do this right now with this compound here. So again, I would start with the ions separately. And so in this case, even if you don't know whether carbon and nitrogen is an ion by itself, you can always look at the reference table. Here we have silver and cyanide. Probably not a combination you would want to ingest. Nevertheless, biggest mistakes were thinking that this was gold. I know it has a G in it. It confuses all of us. There's just no hope. But nevertheless, AU is gold and AG is silver. So just always be careful. And then lastly, the cyanide you would also get from the table. We would see that that is Cn minus. And so to balance out the minus here, you would also just need a plus. And so just like silver, just like iron can have multiple charges or oxidation states, we'll find that silver does as well. And so we will include, that's a set of parentheses with the number 1 in it, or the Roman numeral, to show us what that charge is. I forget what else silver can be. I think it's like 2 common states, things like that. Okay. So that was pretty much the harder stuff on the second exam. What is going to follow through to later on? I would say definitely being given in problems, say, the name of a chemical and being expected to come out with a formula. Similarly, balancing you'll see pretty much now through the next couple weeks. So know that even if you're not great at it now, a little bit of practice will help you a long way with that, which is really great. And there are also some really good tools online if you want to check your work. There are like sort of calculators you can put the equations into. And it's good practice just kind of dissecting each of the pieces and thinking about charges and stuff. Okay. So now we are going to shift a little bit more to chapter 3. I'll try to get through these 4 questions. And then we'll be done with chapter 3, which is kind of exciting. I can hear you in your homes watching this being very excited. Okay, what are we going to start with? 339. Let's start with a relatively simple one. The question here, taken straight from the book, is going to be how many moles of nickel do we have? And again, I'll use the abbreviation MOL for moles. And I'll use the abbreviation for nickel, NI, in 17.7 grams of nickel. And so this, as simple as this may seem, if you can do this, I promise that you can do the rest of this entire chapter. All that we really want to do in this chapter is go from grams to moles, moles to other things, and then usually back to grams. So if you can sort of think about how to set this up, you'll be really well set. And right, all we're developing here is what's known as an atomic mass, which is pretty much the same thing as a molecular mass. It just, in this case, only refers to a single element or atom. If this was Ni2, which it can't be or wouldn't be, it would then technically be a molecular mass. So we just want to set this up, right? The nice thing is we're literally only given one thing in this problem, so we know that that is going to start us off. I always like to just put it over 1 so it's nice and balanced. You are welcome to not do that. And we know we're going to do some math in between, but I also like to just put what we want at the end so we know where we're heading. It's like when you're using Google Maps and you don't actually start the route, and then you kind of can't find where you are because you've moved. Anyway, how many grams of nickel do we have? What did I do wrong? I want this. That's what I did wrong. See, it's not as easy as you think. So the nice thing here is that you can use these units to help you set up what you're going to do next, right? We know that a lot of this math that we're doing is about canceling things out. We know we want to get rid of grams. We know that we want moles. So one way to do that is we can put grams on bottom and moles on top. And then we can look at this different ways, but essentially, right, we know that, for example, if 2 over 2 is 1, or if smiley face over smiley face is also 1, then in this case, grams over grams will just be 1, and it won't affect our math in that way. And so now the hard part is just figuring out what we're putting in here, right? We know that we're starting with nickel. And so we have to think about a relationship between the moles of nickel and the grams of nickel. For that, you are, again, going to turn to your periodic table, which looks kind of sad after I bent it all up. And we can see, looking right in those transition metals, nickel number 28. So I'm just going to take, not the number 28, that's the atomic mass. I'm going to take the mass, atomic number. I'm going to take the atomic mass at the bottom there and plug that in. So the other biggest mistake you can make is figuring out which one goes where, and so you have to think again about how you are looking at how much 1 mole weighs, and that 1 mole weighs as much as the table tells you. So 58.6. And from here, it's really not so bad, right? We could see it a couple ways. We could see it as 17.7. Now the grams are gone, times 1 mole over 58.6 grams of Ni. And that's canceled too. So really it just becomes 17 or roughly 18 over 58. And so we'll be able to find it. Now, before I do the math, I want you guys to think just a little bit about what this answer should look like, right? So that when you're looking at your final result, before you turn it in, you can think about whether you're comfortable with that. So something to note, right? Think about this fraction. It's roughly 18, maybe even 20 if you round up, over something that's roughly 60. So 20 over 60 should be about 1/3. And we'll find that the answer is probably pretty similar to that. I'm going to literally type it into my search bar, because I don't want to get it wrong. 58.6. And we get almost, well, not a third, but we get 0.3, and we'll do 3 significant digits, moles of nickel. Makes sense. Roughly the number we expected. And if you think about it, right, 56 grams is 1 mole, so about 1/3 of that should be about 1/3 of a mole, right? And 58 grams or so is about what you might hold in your hand. I don't know, maybe a stack of nickels, a couple nickels. I don't think nickels are actually made entirely of nickel anymore, but okay. So that is our first. Now let us get through some of the others. So that was 339. Let's move forward. Now we are going to do a percent composition by mass problem. And again, part of the reason we have to do problems like this are because there are scientists and engineers. If we all work together and we're better friends, we wouldn't have to worry about working in either moles or either in mass and whatnot. But we will start in this case from a formula, and then we will work to the amounts or percentages. So going from the molar world to the massive world in that way. CH3, 2, and then let's just do CO. I think this is acetone. This is like what you use to remove nail polish, but you'll get to that stuff in organic if you make it. So where do we start? The first thing we notice is that this isn't a traditional formula, right? This is showing you something about the structure, the way that these are bonded. That's organic 1, that's beyond where we are. So first, let's just make it really simple and put all of the elements together. So let's put C, H, and O, and essentially come up with a molecular formula. Though we could also use an empirical formula for this. So let's just see. We have 1 carbon times 2 plus 1 more, so that's 3 carbon. We have 3 hydrogens times 2, that is 6. And then we lastly have 1 oxygen. And so, right, we are starting in the molar world, and we're going to get to a percent composition, which is to say, carbon is 5% of it, 25% of it, and then whatever's left, the 100 minus those two numbers. Okay, so now what I like to do is think in one molecule, you're going to have carbon, hydrogen, and oxygen. You will have 3 of these, 6 of these, and, just 1 of these. And now we can multiply them by their masses to come up with not only a molecular formula, but the total mass of one molecule, which is really how we define it. So for carbon, we look back at our table, and we have the mass of 12.01, right? That's AMU. We then have for hydrogen 1.008 AMU. And then for oxygen, I think we'll use 16.00 AMU. And so then it just becomes a question of doing that math. And so let's see. I think I can do the first one. That would be 36.03 AMU total, right? That's per 3 carbon. Then we have 6 times, I don't know the 8 times table that well. 6 times 1.008 is 6.048 AMU. And then last but not least, we just have our 16. So then I will total the AMU, which here also kind of becomes the grams per mole. Right? There are this many grams that we'll sum in a moment per every mole of acetone. Okay, so I'll just return to my calculator. We have 36.03 plus 6.048 plus 16. We have a molar mass of 58.08. And so now that we know what the total weighs, we can now take these individual weights and determine our percent composition. So the nice thing is to get the percent of carbon, for example, you need only the amount of carbon over the total amount. And so now you have these two numbers. So let's do all of these. Oh, and then times 100 to get us to the percent. So let's do percent carbon, percent hydrogen, percent oxygen. So the nice thing, right, you're just taking what you've already calculated and dividing it through by the total. So in this case, I'll take 36.03 divided by 58.08, and then I'll multiply that whole thing times 100. Careful not to multiply just the bottom. That is a common mistake or error. Let me set these others up before we're done. 6.048 divided by 58.8 times 100%. And then lastly, 16 divided by 58.08. And you should get 3 different percentages for carbon, hydrogen, and oxygen. And one good test is that they should equal 100%, right? There's nothing else in here. So if you sum up all the parts, that's the way that should come together. And so let's see. We have 36.03. I'm not typing that into anywhere. Divided by 58.08. And here we have 62.03. So this is the mass percent. Let's see what the hydrogen is, try to guess what the oxygen is, and then calculate that one. So here we have 6.048 divided by 58.08. I keep forgetting that. That is only around 10%. Around rounding. And so let's think, well, if it should be 100, hopefully our number comes out to be something like 100 minus 60, which is 40 minus 10. So somewhere around 30 would be what we're looking for. And so, last but not least, 16 divided by 58.08 is around 28. So that's not so bad. You may find at times that it doesn't add up to 100 perfectly. Like, for example, if you do this math here, you can see that it actually comes to 99.9. And that's just because of some of the rounding errors that happen. So best would be always to use the most significant digits until this last step. But know that in chemistry, 99% is often the best you'll get, which is part of the yield question. Okay, that's pretty good. I think my computer is on its last legs, but we will try to do at least one more. Otherwise, in the fourth homework, you guys were given some other sample problems from chapter 3, maybe even some of the ones I've done here. I forget if I doubled up on those, but that'll be good, I guess. And so, let me choose one more to do. Oh, I did. Oh, I have 3 up there. Yeah, let's jump forward to one of the balancing ones. Okay, so now we're going to do 3.113, but know that these others would be good to review as well. Okay, so one thing you may know about chlorine is that it is used in bleach. That's one of the main components. It's one of the reasons you never mix it with ammonia when you're cleaning, because it can form chlorine gas. But nevertheless, they also use actual chlorine gas to bleach cloth. So this would be industrially, for example. One of the ways this is done, or one of the ways you destroy the extra chlorine, is through this reaction. So you have sodium 2, and then you have, this is known as thiosulfate, not something you have to worry about just now, though we will play with it today. Then you have the chlorine that you're breaking up. You also have some water. And then you have, this is the products, NaHSO4 2 plus 8 HCl. And so as we begin to get a sense of what is actually going on with all of these reactions, right, take a second just to look. So first thing we see is that when sulfur only had a ratio of, say, 2 to 3 oxygens, now it has 1 to 4, so that's changing. But also importantly, right, the goal is to destroy chlorine, which is dangerous, and put it in perhaps, well, HCl is pretty bad, but at least it's contained, it's not a gas, right? So you can think about sort of breaking up this neutral compound and making chlorine charged. And as we discuss in chapter 4, things about changes in charges, we'll begin to see why all of this is so important. And so, conveniently, I've given you the balanced reaction. This is 5 elements is a lot, right? 5, 1, 2, 3, 4, 5. I probably wouldn't ask you to balance something as complex as this. So in this case, we'll start with what we have. And so let's start with the question, how many moles of H2O are needed to react with 0.12 moles of Cl2. So, what is the question actually asking? It's asking if you have 0.12 moles of Cl2 compared to, say, 4, how much water would you need? So this is actually not so bad. It's asking about a mole-to-mole ratio. And so we can actually set up a simple relation between them. For example, in the reaction, you know that 4 moles of Cl2 needs to react with 5 moles of H2O. And so in the question, right, this is essentially given in the problem. And now we want to think about the given in the specific question. So now we have 0.12 mole. And what we don't know is how much water we need in terms of moles. And so there's a couple ways to work with these fractions. One thing I like to do is, well, to sort of, I believe the technique is actually to go across that way. So let's do, say, the 4 moles first. Here we're going to see that 4 moles of Cl2 times the unknown moles of H2O is going to be equal to the other zigzag in this, so the 0.12. And then if I have room, I will also put the 5 moles H2O. And so let's just see what that math comes down to, right? It's just 4x, in this case, equals 0.12 times 5. And you can see, right, there's some sort of balance going on here. You have the amount of the chlorine, the amount of the chlorine, the amount of the water, the amount of the water. And we'll find that this plays in a lot in Chapter 4 as well when we talk about dilutions. So the only other thing we would need to do is isolate for x. So 0.12 times 5 over 4. So let's plug that in and see what that looks like. This is 0.12 times 5 divided by 4. And so the number we get out for x, let's now see if it's a reasonable idea. First of all, let's think about what units we're using. So we were talking about moles of H2O, right? And so we can see now that starting with 0.12, we need 0.15. And that actually looks pretty right? Think about the relationship between 4 and 12, right? You would multiply it by 3. And so 5 times 3 would get you to 15. I know I'm ignoring the decimals, but just to show you that the relationship is still there. And so to answer our first question, we need 0.15 moles. Now our next question, I want to do a harder one that's actually not here, just so we can go through it one more time. So let's do a limiting reagent question. Oops, what was that? H2O? Oh no, 1 second. Just 8HCl. So here's a really good process safety question. So let's say you work in a plant and your goal is to make sure that no Cl2 gets out. And so you want to make sure that Cl2 is never in excess in your reaction ever, right? Because then it could get it into the public and kill people. So we're going to do a limiting reagent question where we determine whether or not Cl2 is limiting and whether or not we have a problem. And I will actually make up the amounts and we'll begin to see. So let's say that given 10 grams of the sodium thiosulfate and 5 grams of chlorine, do we have no chlorine left? Can we be sure that chlorine is the limiting reagent? And so we're going to go first to moles, and then to the other moles, and then to the product. But we'll see in just a moment. There is one thing we have to think about, which is that water does play a part here. If you had no water, you would have no reaction. So let's just say that we know that there is an excess of water. And so that could mean that there is 10 times as much as everything else, right? Just like when you're cooking, you often have mostly water in certain things. We'll imagine that here as well. But we don't know yet which of these are in excess. And so the question is going to be, how much of this HCl can we make with each, right? We could also do the other sodium compound, but let's look at what it is we're interested in. And so we want out how many grams, or moles, I guess, but grams will work here, of these. And so we want to go from what we have here over to our grams here. And this should resemble pretty closely what we've seen in class. What we'll do specifically is figure out which is the limiting reagent, again, by figuring out which makes less of this HCl, right? Because in theory, if it is the sodium thiosulfate, you could have excess chlorine, and that could be dangerous. Okay, so let's set up the first and the second one, and then we'll figure out that it's really not so bad. We know that we start with our 10 grams, right? And on this one down here, we only start with 5 grams. Let's do chlorine first because it's a little easier, and you've actually worked with this in class already. So our goal is to get to grams of HCl. How do we go from grams of something to grams of something else? Well, we're going to use our equation, but first we need to get to moles because that's what the equation uses. So the first thing we will do is hopefully get rid of these grams and hopefully transfer just to moles of that same compound. And so, right, we're going to think what's the relationship between these. It's not in the equation. We're going to look back at our table. Chlorine, we know, is 35-ish. And so we will use 70.9 grams of chlorine. Wow, those look like the same letter. To every 1 mole of Cl2. Now that we're in moles of Cl2, we can finally use the equations we have, right? We know 4 moles equals 8 moles here. And so let's set that up. So in this case, I'll say it again, 4 moles of Cl2 equals 8 moles of HCl. So one thing to think about when doing these problems is you're going to start with what's given in the problem. You're going to look at the periodic table to figure out its molar mass. You're going to look at the reaction. And then the last step will also be looking back at that periodic table and coming up with a molar mass for here, right? Because we are in moles of HCl right now. And we want to be in grams. That was always our goal. So last but not least, we just need to know, right? Well, Cl we said was 35-ish, and H is 1. So let's do 36.5. And then, I did it in the wrong way, right? Here we have 1 mole for every 36.5 grams. And so at this point, once you set it up, it's just multiplication, right? So you can multiply everything on the top and divide through by the bottom. Let's do that before my laptop dies on us. We have 5 times 8. 5 times 8 times 36.5, all in parentheses, divided by 70.9 times 4, and that's it. And I get out 5.15. So at this point, I don't know if this is the limiting reagent or not. I hope it is for the safety of our imaginary problem. But here, what we're going to need to do is compare it to the one on top. So now we're going to do really the same exact thing and come out hopefully with a number that relates to how much we have. Okay, so the nice thing is we can use the same forms of the units, right? What can I do here? So I have grams over here, grams of Na2SO3 and 2SO3 to moles of the sodium sulfate. I'll just do NaS for right now. We want to go from moles of NaS to moles of HCl. And then we can even use this same thing, right? Because we want to end in HCl. So there's a couple things we need to fill in. What is the relationship between sodium thiosulfate and our product? Well, here we can see that there is 8 moles of our HCl and only 1 mole of what's going in. Now, in terms of the molar mass of this, well, that's going to take a second, right? We need to figure that out. So let's figure it out. Can you see over here? Yeah. So we know we have 1 sodium. We know we have, that's a lie, we have 2 sodium. We know we have 2 sulfur. We know we have 3 oxygen. And I admit, even I don't remember sulfur's molecular mass, or atomic mass. 32. And that's oxygen, if that matters. 2 sodium are 23 each. So, right, I'm going to add up all the individual contributions. Let me do that just here. We have 2 times 23 plus 2 times 32 plus 3 times 16 gives us 158. So now we can throw that in here as well. And the nice thing is now we can calculate everything that's on top. So let's do that together. We have 10 grams to start times 8 times 36.5 divided by 158. It's that simple. And we have bad news, I think, at least for the safety of the problem. So we come out with 18.5 grams of HCl, which is telling us that because with chlorine you can only make this much, that there is an excess of sodium thiosulfate. And, well, actually, that's good news. That means that we're fine. So, in this case, the smaller number is always the limiting reagent. And so because chlorine is limiting, we will have none of it left behind. And then, in theory, none of it can escape to poison the town, or whatever it was in this scenario. So I apologize for my computer dying, but that's actually about an hour anyway. So hopefully we're good. If you have any questions about other problems, you know where to find me. Otherwise, I will see you guys next week. And I would say start doing some math now for our exam in 2 weeks, because it'll catch up on you. It always does. Have a good week, guys.